to introduce myself. I'm David Bao, and I'm assistant professor at Northeastern University. I'm also director of the NSF National Deep Inference Fabric. And today I want to talk to you about a topic that I think is really important as we build out large-scale AI, which is resilience. Resilience is super important because AI is really integrating into society very quickly. It's getting adopted more quickly than almost any other product in history. And we are investing unprecedented amounts into scaling up its infrastructure. And yet, if you go to any of the experts creating AI, you get these odd messages like this, where people talk about how we actually have no idea how the AI is actually working, which leads to this question, are we building a brittle world? And to sort of put the framing in context, I want to say, AI is not a totally new thing. We have very complex systems that we've made in the past. And so what I want to start off with is taking a look at an example of how we're dealing with resilience with a traditional computing system. So I don't know how many of you were impacted by the CrowdStrike disaster back on July 19th last summer, 2024. So I was traveling on my way through Europe, and I was in an airplane when CrowdStrike happened, and they took the airplane out of the air as all the airline systems went down. And so I got stuck in the city of Zurich. And the interesting thing was that the impact of CrowdStrike was actually quite broad in society. It was impossible to check into a hotel that night because CrowdStrike killed Windows installations across the economy. And so the CrowdStrike patch killed a huge number of hotel systems, and they weren't able to look up my reservation. But beyond that, they couldn't take charges, but there were also bizarre things that they weren't able to do that day. They couldn't even open up the rooms. The keys to the rooms were all electronically controlled, and with the Windows systems all down, they couldn't open up the rooms. They couldn't control the heat in the hotel. They couldn't control the light. They couldn't contact their employees. You could ask, how could that system have been better? But I think that's the wrong question, because resilience is not a question about the technology itself. The resilience is about the ecosystem. And so what I want to talk about today is how can we make an ecosystem around AI that can sustainably adapt to unexpected challenges. So resilience is one type of robustness. There's really three types of robustness that we typically talk about when we are looking at technology systems. The three R's. We talk about reliability, we talk about robustness, and resilience is really the third kind of R. And so what's the difference between all these? Well, reliability is really about reliability and expectation, how well a system performs on average. So when the hotel says, we have 20 years of experience running our hotel software, they're talking about how they found it to be reliable over time. And in AI, it's really our bread and butter, maximizing the expectations of reliability of these systems. That's how all of machine learning works. We evaluate AI, we benchmark it. When we train it to maximize its behavior in the expected average case. Now, the other two R's are a little bit less mainstream for AI scientists, but they're really important. Robustness is about worst case performance, is about anticipating what could go wrong instead of worrying only about what's going on in the average case. So for example, if you go to the Hyatt website and you look up how they're doing with the security of their hotel software systems, they'll point out that they've patched CVE 2023-20 which is a bug that they found, identified, and fixed in their Opera Hotel Management System. And what this is they're looking for what kinds of security vulnerabilities or what kinds of serious bugs might be present in their system. They're trying to anticipate what could go wrong by red teaming the systems, by stress testing them, by putting them in adversarial situations, and then trying to fix things before the problems happen. And in AI, we are doing this also. We have a number of different efforts which are very important for red teaming systems and patching the systems and trying to design AI in a way that can avoid problems that we can anticipate ahead of time. So if once you've got reliability and robustness, what else is there? What is resilience? Well, resilience is the third R. It's about the ecosystem response when there's an unexpected challenge. So unlike robustness, which is about trying to anticipate what the problem might be, resilience is trying to figure out how to make the entire system, the entire ecosystem perform well, even when something wrong happens that you didn't anticipate ahead of time. In the hotel systems case, when the hotel system goes down, for example, if the patching system that you were using to try to ensure robustness is exactly the thing that pulls the hotel system down, well, that's sort of an unexpected challenge. Can the hotel keep on running anyway? And resilience is difficult. It was difficult for the hotels on that day. It was difficult for me as a hotel guest. I showed up at the hotel. The entire lobby was full of 100 guests that should have been in their rooms, just sitting in the lobby, waiting for the hotel staff to try to figure out how to run this hotel with windows completely knocked out. In AI, there are certain things you need to invest in to get resilience, and I'm going to use the hotel story as a little bit of a framework for understanding what they were. So now the interesting thing is the hotel was able to get back on its feet after a few hours, and they started forming lines and getting people checked in and getting them into the rooms. And the reason they were able to do this was because there were things that the system was doing that the hotel staff knew how to deal with even when the system was malfunctioning badly. These were things where the hotel was really resilient on. These were things like payments. These were things like opening up the room keys. To get into rooms, the staff understood what the problem was that had to be solved. They had to figure out how to open the doors. The second thing that they had that allowed them to solve the problem was they had control. It turns out that they had a master key that they could use to open up the doors even if the electronic system wasn't opening them. And they had the permission to do it, which is the third thing that they did. So they were able to take payments and then they were able to open up rooms. It was a pretty major decision for the hotel to give the hotel staff power to take payments because some of the guests would say, hey, on my reservation, it says that I have to pay more. And other guests would say, my reservation says I have to pay less. Other guests would say, oh, I've already prepaid. And without access to the computer systems, the hotel front desk staff had to make on the spot judgments of who to trust. And it would have been very easy for the head office to say, we don't trust you with this. We don't give you the power to take charges without the computer system on. But they did. So even though you might have an understanding and control, it's equally important for you to have permission to do things in order to have resilience. So these are the ingredients of resilience, and I think that this was a pretty good experience getting back into the hotel after a few hours. Um, but let me tell you, staying in the hotel overnight was actually a pretty bad experience on CrowdStrike Day. And the reason is because in the middle of the night, every couple of hours, all the lights in the hotel, including all the lights around your bed, would suddenly turn on, and all the heat in all the rooms would simultaneously turn off. I went down to talk to the front desk and asked them what was going on, and they had to explain that they were not able to fix the problem because they had no idea what it was the system was doing. They did not understand this particular function of their Windows hotel management system. And then I asked them, well, can you just turn off the electricity? I'd like to be able to sleep in the dark. And they said, no, there's no special control. The computer system is in charge of this, and we don't have the ability to change it. Can you just turn off electricity to all the guest floors? And they say, no way, we have no permission to do that. That would be a safety issue. So without understanding, without an ability to control, and without permission, they were not able to achieve the kind of resilience that they would have to withstand a badly malfunctioning system. So how is this all related to AI? So what we're building with AI is really a new kind of technology where all these problems that we had in the past have been amplified. And one of the core issues is that in AI systems, since they're not created manually by human programmers, the people who make the AI systems don't have a detailed understanding of how they work. It makes resilience a special kind of challenge. And so, what I'm going to give here in the rest of this talk is a little bit of a status update and advice on the kinds of things that we should be investing in as an industry in AI. And the first thing is to improve our understanding of how AI works. And I'll give you a little sense for what kinds of things that we're doing in research to try to improve understanding of AI. So when you use a big chatbot system like ChatGPT, it's a next word prediction system. If you have a partial sentence like Miles Davis plays it's the way the system works is it will do a whole bunch of arithmetic to analyze the words that have been said so far, and then it'll predict the next word, which in this case, it'll predict the word trumpet. And the amazing thing about this is that somewhere in all of those calculations, it must be encoding this knowledge of who Miles Davis is and what instrument he plays. But because all of these connections are trained through an opaque optimization process, people don't really understand what the knowledge is or even where it might be inside this big AI. But it is possible to figure this out. And the kinds of experiments that we run to do this is we typically will run the model twice, where we run it under a different condition where we say that somebody else is playing a different instrument, and then we ask, is there information that we can capture in the neural states and transplant them from one run to the other that eventually cause the model to recover the idea that somebody is playing the trumpet. And what this kind of experiment does is it allows you to localize where the knowledge is inside an AI. I'm not going to go through all the technical details of how these kinds of experiments work, but I'll show you some of the kinds of readouts that you can get. So for example, in this simple experiment where you take a look at how the model might know that Shaquille O'Neal plays a sport of basketball or that Megan Rapinoe plays a sport of soccer, you can localize which neurons are responsible for resolving that information, and you can find that the neurons that are involved show up in two specific locations with two specific purposes. One of the locations resolves the knowledge of who the person is, and then the other one determines the word that you're going to use to utter the answer. And so at this location A, you can see that it really generalizes over a large number of different types of facts. We can start to localize where the knowledge is inside these things. Dealing with AI software is a bit different from dealing with traditional software. You need to construct special experiments for probing their internal structure if you want to understand how they're constructed. And it's a bit like studying biology. Just like biologists have been able to understand the structure of how emergent living organisms work by carefully putting together experiments, we're able to understand a lot of what's going on in AI as well. We've only been at this for a few years because large-scale AI is so new, but we're making pretty rapid progress through it because setting up experiments on AI is quite a bit easier than setting up experiments on like a physical biological system. So we're able to localize things like knowledge, and we're able to localize many other different types of activity going on inside these networks. And what's really emerging is really a three-part, what I'd say is understanding AI is really turning out to be a three-part research program. The first big research question is to ask what information is encoded in the neurons. Um, so for example, in this sentence, Miles Davis plays the trumpet, there's a particular location which seems to encode all the properties of Miles Davis. The fact that he's a musician from a certain era, playing a certain instrument in a certain geographic region, and understanding what kind of information is encoded and how to decode that information is really the first step of understanding what's going on in AI. But in addition to information, what you find is that there's knowledge of how different information is associated with other information. So for example, if you have a person, Miles Davis, and you associate that with the idea that they play the trumpet, um, that turns out to be stored as vector maps, maps inside the AI that go from one set of vectors to another set of vectors. And mapping out these maps is really the second type of map that we need to create in understanding AI. And then the third type of thing going on in AI understanding is understanding the pathways that information takes over long periods of time. The long pathways, which are really the algorithms that an AI uses to understand what's going on. And uh, so the field of AI interpretability is really coalesced around these three types of problems, and in a lot of different ways, we're making progress at understanding. So let me give you a little sense for the second ingredient for resilience, which is control. Let's say we understand how knowledge is encoded in a network. Well, what that allows us to do is it allows us to say, well, maybe some of this knowledge is wrong, or some of the knowledge is out of date. Well, if we know where the knowledge is stored, instead of having to create a completely new AI that might have some of the knowledge changed, maybe trained on different data, if we can localize where the knowledge is, then ideally we'd be able to do something equivalent to a database update, like go into the knowledge and actually find an association pair and change it. And one of the things that we've been able to show is that you can actually do this. So in the paper Locating and Editing Factual Associations, we show that you can actually uh, identify where the knowledge is for some fact, like the Space Needle is located in Seattle, and then you can move it to a different association. Like you can get the model to believe that the fact is something new, something different, like the Space Needle is located in Rome, by just changing neurons at a very specific surgical location. And the interesting thing about doing this is that we found that with an understanding of where the knowledge is, we can make these surgical changes more precisely with better precision and generality than you can if you tried to do traditional fine tuning to achieve the effect, or even if you used sophisticated meta learning techniques. So you might think, well, why do we want to move the Space Needle to Rome? Um, well, let me give you an example of something where you might want to fix things in a real world scenario. So in diffusion models, I don't know if you've noticed how diffusion models tend to produce output like this, but in a diffusion model, they contain all sorts of knowledge about what different things look like. So let's take a look at an example of producing an image like an image of some doctors. Inside the diffusion model, you've got several steps. First, the query, like I want some doctors, gets turned into a neural vector, which I'm going to put here as K, which encodes the text that means what your query was, that you want some doctors. And then that goes through cross-attention maps that map that vector to another vector, which I'll call V, which really encodes um, the appearance of what doctors look like, and then it goes through a whole diffusion process that ends up synthesizing an image that looks like a photorealistic image of doctors, like what's on the right. So this is all fine until you look at the images and you realize, holy cow, the doctors always end up looking like this. It's pretty hard to ask the model to generate a picture of some doctors and get any female doctors out or get any minority doctors out. What's going on here is that diffusion models are well known as suffering from a problem called bias amplification, where not only do they reflect the biases in the training data, all training data has lots of different biases, but they tend to amplify those biases dramatically. So if there's a slight tilt away from female to male doctors, then the diffusion models will tend to strongly amplify that tilt and almost completely eliminate the female doctors, amplifying the biases that were already present in the training data. And so how the heck do you fix this? If models are amplifying biases, then it's very difficult to try to rebalance the training sets and retrain all these diffusion models to try to get rid of their biases. It's devilishly hard because it's very unpredictable what the effects will be of changing the training data one way or the other way. If you try to rebalance one type of bias, then invariably you'll introduce a different kind. And worst of all, it can take months to retrain one of these models because of the huge data volumes and costs involved in doing large-scale um, AI training. But what if you could understand the systems and control them better? Well, what you can do is you can use the exact systems that I talked about in the Rome method for editing knowledge directly. Uh, we can take this mapping of text that means doctors to a vector that means male doctors or what doctors look like and change that mapping to go to a different vector. So now the vector that we want is like a vector that might mean half male doctors and half female doctors. Where the heck do we find a vector like that? Well, you can hypothesize. So first of all, it's pretty easy to get a vector out of the model that means this is what male doctors look like. It's a regular vector that the model maps the query to. It's actually also really easy to get a vector out of the model that represents what female doctors look like because you can enter a text prompt that says, give me some female doctors, and it'll be happy to do that. But if you just ask for generic doctors, then what you'd ideally want is a diverse mix. And so what vector would encode that? We can easily hypothesize that the vector that is an equal mix might lie on the line between the vector for male doctors and the vector for female doctors. So what we do is we grab a vector that's on this line and we do a Rome style edit to change the neurons that represent the mapping from the text that means doctors to what doctors look like. Because the Rome style edit is localized to exactly where this mapping happens, we can do that in a fraction of a second. And then we can test it and we can see, what comes out. And because this process of editing is so lightweight and so quickly, we can actually do a grid search to find a vector that leads to the type of diversity and the behavior that we actually want. In the example on the right, not only am I doing a grid search over gender, but I'm also doing a search over race as well. So you can do this to fix biases. You can also do this to fix copyright issues. You can reduce sexual imagery in these models. It's actually a very practical technique. If you can localize this knowledge using these kind of methods, you can actually scale this up to be able to change hundreds of facts in a model really quickly. So the last thing I really want to talk about is power, which is a little bit of a strange topic for a technical discussion. But the interesting thing about the structure of how we make modern AI is that we tend to mix up two things, which is one, there's this hugely expensive process of pre-training a large-scale foundation model to absorb all the world's information. And this pre-training process can take many months, it can take many billions of dollars, and what you end up with is a system that really can't do much except for complete sentences and complete documents, but it does seem to encode a huge amount of knowledge about the world. So it's sort of where the brains of the model come from. But then the second phase is you give a personality to these systems using a fine-tuning process using RLHF. And this fine-tuning process is a lot lighter weight than the pre-training method. The amount of electricity it takes is far less, and the kind of data that goes into it is much more editorial in nature. What are the biases? What are the safety measures that we want to take in this type of thing? So all of this sort of interpretation and control technology also is in this sort of second category. Um, and so the thing that is difficult is that as a safety or as a resilience kind of person, there's not a lot that you can do with that first phase. But what you really want to do is have some more control over this second phase. But the problem is the capital cost of getting involved in the second phase is quite high. It's almost as high as the capital cost of getting involved in the first phase as well, because the kind of computer systems that you need to have to fine-tune systems, are quite large. The minimum cost it takes to do any type of training for a large-scale system can be like $1 million or so. As a result, we're not really doing a good job at studying large-scale AI. Most of the work that's being done to study interpretable systems and how to control these systems in detail are done on much, much smaller systems than the large-scale commercial systems that are being released. So what I want to talk about for this third thing is how to create an ecosystem that gives people the power and the permission to study how big models work so that we can build the technology for building resilience that really works in practice. And so this is what I want to introduce here is the National Deep Inference Fabric, which is an opportunity to build an AI research ecosystem by building a technology layer that allows us to, to do transparent research in that second phase without the barrier of having to invest in individually the huge capital investment it takes to get involved in that second phase. So NDIF is made of three things. It's made of software, computational capacity, and educational training materials. And the idea of NDIF is it does the costly engineering for getting involved in the fine-tuning and interpretability and control phase of AI all once. We build these systems. They are a special type of inference system, which we call white box inference, which is a little different from the typical inference systems that are used in regular commercial AI. So in commercial AI, you build black box inference, which means that you can give inputs to a system and get outputs, but you don't get any visibility into what's going on in the middle. In the National Deep Inference Fabric, when you give the AI an input to run, you also give it a scientific payload, which in this little diagram, the scientific payload is this little yellow box. It's like a little piece of Python that is actually designed to run on the inside of the AI instead of the outside at the same time that it's executing your AI request. And the National Deep Inference Fabric will run the AI, but it will also at the same time run your customized scientific payload without you needing to take custody of the entire model. And so that solves several problems, but the key problem that it solves is it relieves you from the capital cost of having to have complete custody and complete ownership over the cluster that is running the AI that you are probing, that you're customizing, that you're studying. So if there's a large scale AI that many people are interested in, with the NDIF infrastructure, they can all share that AI and study it at the same time without everybody having to have their own custom copy of it. It gives every control full control over models at the trillion parameter scale. You can control every step of the computation. You can inspect how the model is behaving and storing and retrieving and computing on every piece of information in all of its intermediate steps. And you can use this to map out and control a model's knowledge. And so NDIF we look at as a key piece of scientific infrastructure to enable people to develop detailed human understanding of massive AI models. It's a community resource that's designed for scientists to participate. Our goal is to create a scalable scientific community to build expertise on how to look at AI internals like this. And I'm going to skip over the detailed examples of the NDIF API. We're quite proud of the technical design of how this works. But suffice it to say that it's extremely flexible. Basically, any scientific experiment that you would want to run on a large-scale AI, you can encode by writing a little piece of PyTorch and sending it into the NDIF server. We have lots of tutorials online for you to try it. And what I'd really like to encourage you to do is, if you are interested in building interpretability, control, and resilience for large-scale AI, then come and get involved in the NDIF community. Here's a few links on where to find information about it. You can use it today. The system is up and running. We support people using it on our Discord. Just come and get an API key. And in addition to this, we have a special early access pilot program that has expanded support for new, larger, and more diverse types of AI models. If you want to apply to this program, it's pretty straightforward. We're looking for special research partners to help us test out the new system. So there's a form here at ndif.us/hotswap.html where you can sign up for these types of things. Right now, the NDIF is on a 4-year development trajectory. In this year, we are building code-free user interfaces that you can try out, that you can use to take a look at the inside of the systems even without writing any code. And our goal is to continue to build the system so that infrastructure like NDIF becomes broadly available as a way of allowing us to build AI to be more understandable, more controllable, and more resilient over time. Thank you very much. Thanks for watching. Thanks for joining us today. And I hope you enjoy the rest of the CSA program.